in this session speaker, Professor Ignacio Lira, Ignacio Lira, Congulhem? Ignacio?
Yeah, no, you don't have to say that. Just Ignacio Lira, it's enough.
Ignacio Lira, yes. Professor titular honorario of Pontific University, Catholical University de Chile, Chile, Santiago. You have presentation. Assessing measurement uncertainty in nanotechnology. Insights from SEM and DLS techniques. Ignacio, please load your presentation.
Hello, everyone. It is a pleasure to be here.
Yeah.
I thank Dr. Sakharov for organizing this conference and for inviting me to participate with this talk. As most people know, nanotechnology is becoming more and more important, especially when it comes to the different ways we can use nanoparticles. However, it looks like there hasn't been a lot of research focused on evaluating the uncertainty in measuring the size of these tiny particles. So today I'd like to share some thoughts with you on how we might tackle this issue. I'll specifically dive into two common measurement techniques: scanning electron microscopy and dynamic light scattering, or for short, SEM and DLS. So let us now set the scene. If you look at this slide, you can see that nanoparticles are incredibly tiny, about the size of a virus or even smaller. But despite their small size, these little elements can be used across a wide range of industries, from agriculture to textiles and everything in between. In each of these applications, size is a key characteristic. So that's the reason why there are so many techniques available to measure it, to measure the size. So, as I mentioned earlier, we'll take a quick look at the basics of two of these techniques: electron microscopy and dynamic light scattering. Actually, electron microscopy has two main branches: scanning electron microscopy and transmission electron microscopy. Today I'll focus on the former, but what I'll explain also applies to the latter, with just a few tweaks, as one might say. Both techniques, of course, need an electron microscope, which is quite an expensive and complex piece of equipment. Technicians need to be very highly trained to operate it. On the other hand, the setup for dynamic light scattering is much smaller, more convenient, more affordable. It needs a comparatively inexpensive desktop equipment like a computer, and it doesn't require as much training. But another difference between the two techniques is that electron microscopy is a direct measuring method. It is a bit like using a ruler. It measures individual particles one at a time. In contrast with dynamic light scattering, we look for the average size of a group of particles instead of measuring them individually. So you might be wondering why a lab that focuses on one of or both of these techniques would want to figure out their measuring uncertainties. Well, probably most of you know that this is important for a number of reasons. For example, in quality assurance, this is important for helping ensure that the data obtained are reliable and accurate, which is crucial in research and industrial applications. For reproducibility, allowing other researchers or laboratories to reproduce results, which is essential for validation and comparison of findings across different studies. To comply with standards and guidelines like ISO 17025, which may even be mandatory in some cases. To assess the impact of potential errors on experimental outcomes, and thus helping to manage risks associated with nanoparticle applications. For process improvement, because by identifying sources of uncertainty, labs can optimize measurement processes and techniques, so leading to better quality products or results. For customer assurance, because transparent reporting of measurement uncertainty builds trust and confidence in the results provided. For decision making, because accurate estimates of uncertainty help in making informed decisions based on measurement data, particularly in critical applications like pharmaceuticals or environmental monitoring. And also for scientific integrity, because documenting measurement uncertainty reinforces the integrity of scientific research, ensuring that findings are presented with appropriate caveats regarding their limitations. In summary, evaluating measurement uncertainty is vital for accuracy, reliability, regulatory compliance, and the overall credibility of the lab's work. Now, as we all know, to apply the gamma uncertainty framework, we have to start from a measurement model. As we will see, for DLS, the model is quite straightforward. But on the other hand, since SEM is a direct measurement technique, the model has to include the calibration of the instrument and the correction factors that account for possible systematic effects that may arise during measurements. So let us start by looking at how DLS works. And this technique uses an expanded laser beam, inexpensive laser beam, that hits a sample that contains the nanoparticles diluted in a medium whose refractive index n has to be known. That light gets scattered in all directions. A detector is placed at a specific angle theta relative to the incoming laser beam. Since the particles are in Brownian motion, the intensity of light that reaches the detector varies. So it is possible to describe these light fluctuations using an autocorrelation function that has an exponential decay gamma. This decay rate is one of the key inputs to the measurement model, which I show here. The model allows to determine the mean hydrodynamic diameter d of the particles in the sample, defined as the diameter of a hypothetical hard sphere that diffuses with the same speed as the particles under examination. The diameter is also a function of the scattering angle theta, which is included in the constant S, the temperature T of the solution, its viscosity mu, the laser wavelength lambda, and the term C, which depends on the Boltzmann constant Kb. Applying the law of propagation of uncertainty to this model is quite straightforward. The only tricky part here is that both the refractive index n and the viscosity mu are not independent because both depend on temperature, and moreover, the refractive index depends also with the wavelength of the laser. Fortunately, it is possible to demonstrate using known data to demonstrate mathematically that the wavelength dependence is quite weak and can thus be ignored. Then we use correction factors F that account for the uncertainties in the published viscosity, F mu, and refractive index, Fn, as these properties relate to temperature. This approach results in an equivalent temperature that incorporates the actual temperature along with the derivatives of those two functions with respect to temperature. The GAN procedure applied to this DLS model is quite straightforward, as you see by this long expression down in the slide. However, there are two additional challenges that need to be considered. First, the measurements can be affected by multiple scattering, meaning that the results would vary depending on the concentration of the particles. The second challenge is that the choice of scattering angle also plays a role in the results. Little literature is found about these two effects, so I believe that more research is needed to find a way of incorporating both of them into the model. Now, let us look at the models one can use in electron microscopy. In length measuring instruments, one needs two models, one for the calibration stage and another for the measurement stage. The former, the calibration stage, involves figuring out a calibration factor F, which is the ratio of a known distance to the distance that is indicated by the instrument. This is general. In electron microscopy, obtaining this factor is a rather tedious operation. And for this reason, many laboratories do not go through it. They just use the calibration factor provided by the manufacturer. But then it would not be possible to calculate the measurement uncertainty. So let us briefly explain how the calibration factor is obtained. For this, one uses a calibrated measurement standard. Here I show a typical standard used in electron microscopy. Notice that it is very small, only 1/10 of a millimeter in size. It features a series of patterns whose bars are separated by known distances. These distances have to be certified by a higher level laboratory. So when one buys such a standard, it has to come with the certification of the distances that are detailed on the standard. When using the microscope, the technician must choose one of these patterns. The selection is based on the magnification he or she plans to use during the actual measurement stage. We refer to the chosen line separation as the pitch P. For example, suppose the user selects the largest pattern whose known pitch is 2 micrometers. He or she then uses the software of the instrument to draw a straight line perpendicular to the pattern that covers n pitches. The length L of this line in physical units, micrometers say, is given by the number of pixels in that line, ns, as indicated by the instrument, times the pixel size, LP. This would be the indicated distance. But to find the pixel size, the user obtains the number NP of pixels in the scale bar, which is this white line down here, printed in the measurement standard. This number of pixels is used to divide the known length of the bar, which is 10 micrometers in this case, as printed down here below. Of course, it is wise to repeat the calibration measurements several times in the other 3 directions, the horizontal one and then the 2 vertical ones, and also perhaps repeat once more for more accurate results. What I just described is the standard calibration procedure. The interesting part comes when we look at the systematic effects that introduce correction factors. I believe there should be at least 4 key factors to consider. The factor due to the thermal expansion of the calibration specimen, Ft, the factor due to the inclination beta of the measurement standard relative to the horizontal plane, the factor due to the misalignment gamma of the measured line L with respect to the bars of the standard, and finally, the factor that has to do with the determination of the edges, both of the measuring line that measures L and also the measurement of the white scale bar printed when determining the number of pixels actually in the scale bar. The estimated value of these four factors, if one, of course, does everything with care, the estimated value of these four factors is 1. But for our purposes, their uncertainties are needed. The one for the thermal correction factor, Ft, is not difficult to obtain, since its model is very simple. Alpha is naturally the thermal expansion coefficient. Instead, for the two cosine errors, we have to resort to the equation in clause F244 in page 67 of the GAM, because the error in the cosine when you go to either side is the same. So this is described, as I said, in this clause F244, which for the benefit of time, I will skip the explanation. Lastly, the correction factor for the edge effects must consider two uncertain influences: the number of pixels in the scale bar and the number of pixels in the measuring line, because there are, as I said, two edges, or actually four edges we have to consider. To handle this effect, I propose using a rectangular distribution with uncertain limits. Again, there is no time to go into the details here. So let us now turn to the actual measurements of the particles in an image. Here I show an image of polystyrene nanospheres. Photographs such as this are, of course, taken by the microscope itself and are generally processed with the software called ImageJ, which is an open source image processing program that is widely used in electron microscopy. That program first eliminates all agglomerated particles, isolates them, and then proceeds to binarize the remaining ones. So they will all look completely black against the white background. Next, the software is able to perform two operations which are called erosion and dilation. These operations produce the minimum and maximum contours of the particles, which I show in this next slide. You don't see them very clearly here, but by increasing the size, you can see that these are images of the same particle, but with the uncertain borders. So the next step is to measure the area of the two images, processed images, for each of the spheres. The area is obtained by counting the number of pixels contained inside of these borders. This pixel size is again the ratio of the indicated scale bar of the image divided by the number of pixels along that bar times the calibration factor. And lastly, the image J, once the areas are determined, by image J, as I said, has to count the number of pixels in each of the two images on each of the processed particles from which the corresponding areas are obtained. So, if one assumes that the images of the particles are circular, we can determine the corresponding model for the average diameter of the processed particles in the sample using these two equations with the square roots. By having the models for the calibration factor and for the measurand, we can put them all together. It is then a rather trivial matter to obtain the uncertainty of the average diameter of the ensemble of each of the particles by applying the Gauss law of propagation of uncertainty. In conclusion, we might say we have explored the significant role that measurement uncertainty plays in the field of nanotechnology, particularly concerning the accuracy of nanoparticle size measurements. As we have seen, both scanning electron microscopy, SEM, and dynamic light scattering, DLS, are valuable tools, each with their unique strengths and challenges. Understanding the calibration processes and the uncertainties inherent in these techniques not only enhances the reliability and reproducibility of the research results, but also fosters trust in scientific findings across various industries. The pursuit of precise measurements is more than just an academic exercise. It is essential for quality assurance, compliance with industry standards, and protecting scientific integrity. As we move forward, I encourage all of you to consider the implications of measurement uncertainty in your work and strive for continuous improvement in our methodologies for evaluating such uncertainty. I refer you to these two papers for further explanation of what I just said. If you're interested, you can write to my email and I'll gladly send copies to you. Thank you very much for your attention.
Thank you, Ignacio. Very interesting presentation, very interesting. Do you have any question to Ignacio?
Well, it's Vladik. Thank you very much for very interesting presentation. The question is that when you talk about accuracy of pixel matching, you assumed, if I remember correctly, uniform distribution, right? When the part of uncertainty that is called by pixel matching.
The uncertainty of the pixel size?
No, the pixel. Yeah. So when you take into account the two different pixel, when you match the pixels on the sample and the pixels over there. Yes. Here. Oh, next. Okay, next. Yeah, here it is. Oh, you slipped it. One less. No. When you have the two, yeah, here it is. When the two bars, right? So you said that you assumed uniform distribution, right?
The one here, up here?
Yes.
Yes, this is the uncertainty in measuring the one of the
Right.
the
So you
borders
assume it's uniform distribution, right? Based on what you were drawing.
Yeah. Yes. Two uniform distributions.
Right. Because this is just an assumption. It's just the question is, will the results change if you have some other distribution here? Like normal cutoff or something.
Oh yes. You can use other distributions, of course, but as always in the evaluating the uncertainty of measurement, you have to have you have to use some assumptions, and the results of things, of course, will vary according to the assumptions you made. In this case, they will vary according to whether you use rectangular distributions, uniform distributions, or other distributions like the normal, which would be perfectly reasonable, but you have to be prepared to explain what would be the how reasonable would be your assumptions.
Okay, thank you very much.
And also using other assumptions, like using other distributions, would imply that the calculation procedure would be a little more difficult or a little more easier. In this case, the easiest way would be to use rectangular distributions.
Okay, thank you.
May I say something?
Yes.
Yes.
Ignacio, 13 years ago, in February 2013, I have a paper with Professor Włodarski from Kiev, Kosovo, and Shantur about calibration of scanning electron microscope for measurement dimensions in the nanometer range. I was not the main author of that, but anyway, this paper is in Polish, but I can send you the Word version, and you can translate it automatically to English. Are you interested in this paper?
Very much, Sigmund. Yes, very much.
All right. Then I send you. I hope that I have your actual address, mail address.
Well,
for any reason, please tell me. Maybe now.
The email is here in this slide, Sigmund.
In slide, and in the beginning, yeah. All right. Well,
no, it's down there in the slide.
But sorry, but something happened and I don't see it now. Just a moment. Yeah. Well, anyway, I am going to just to send. Maybe I can see what I have in my computer. Yes, because, and if I write down Lira, what I obtain, Ignacio Lira, Lira, ing dot put dot cl. It's actual?
Well, right now I'm using another one, but if you use the old one, it would still reach
All
me.
right, then I send it now to you. All right.
Great.
On the old one. All right.
Great.
And
was-
when you obtain it, you can write me your actual address, because I would like to keep a contact with you.
Good.
and you maybe will be again someday in Europe, maybe in Poland also.
Good.
All right, then.
Thank you.
Yes. Well, I sent it anyway.
Thank you, Zygmunt, for your question.
What's the question? That is just.
Dear participant, do you have any question?
Okay.
Ignacio, one question to you. As I understand, you calculate uncertainty type A. Yes?
Most of the uncertainties come from the correction factors, and these are actually type B uncertainties.
On the correction factors.
Yeah. For these correction factors, Fn, F mu. For lambda, for example, the uncertainty of the wavelength of the laser, this is a type B uncertainty because you find it from characteristics of the laser. For the uncertainty of the angle theta, that depends on the machine you use, because you don't put the detector. You put the detector in the place that the apparatus tells you to do, but you cannot apply have many values of the angle theta. So all uncertainties in this expression would be type B. And I think the same happens in the calibration factor of SEM, except that here now you have to measure the pitch. I mean the number of pixels in the lines, in these lines that you have to draw, and here you do have a lot of data that you have to process with the type A method.
Thank you very much. Excuse me, I missed these slides because I have a call in this moment. Can you send me your presentation?
This one, yes, of course.
I have it. Да. Thank you. Dear participants, do you have any question to Ignacio? Victor?
Maybe a short comment or question. Ignacio, you have mentioned several other techniques at the beginning of your presentation, like atomic force microscopy. Are you dealing also with such type of measurements?
No, I'm not familiar with most of the other techniques. I know that there is a paper in one journal, it's probably Methodology, that evaluates the uncertainty in atomic force microscope. But I really haven't read that.
I'm just asking if you personally are dealing with such type of measurements and uncertainty evaluation in this type of measurements.
No, I'm not familiar with them. Let's see here. I wouldn't say that electron microscopy and dynamic light scattering are more important than the other ones.
Yes.
This would be a matter of some more specialized individual that really works with the different techniques. Probably, since most techniques are very specialized, I would say that you wouldn't find an individual that is familiar with all of them. And I am not. I am not.
Yeah, thank you very much. And thank you for your presentation. It was very nice. Thank you.
Thank you, Ignacio. Very good presentation. Thank you. Thank you. And maybe next presentation. I give the floor